Well, we're coming to the end of Chapter 4 of Computational Optical Imaging, which deals with geometrical optical systems. We've talked about coated aperture imaging, projection tomography, and coated aperture tomography. These are all technologies that don't use lenses. They just use obscurants or collimators or coated apertures to form images because at X-ray frequencies, lenses are not available. But we have to have detectors, of course. We have to detect the field that we're going to computationally reconstruct. And this is an example detector for X-ray imaging systems, flat panel detector from Detection Technology. It's a 3000 by 3000 detector array, 30 centimeters on the side with 99 micron pixels. So why did they choose to do this? What makes it so that one would choose to have 99 micron pixels? That's the key issue in figuring out the resolution of the imaging system. Throughout this set of discussions that we have on computational optical imaging, resolution and image quality are key metrics we have to discuss different optical imaging systems. And so we'll always look at, for each system, what determines the kind of features that we can see spatially and temporally in the imaging systems. This is an example of a CT system. Here's an example of a X-ray detector array for dental X-rays, and now you see the pixel size is smaller, down to 18 microns. And of course, the device has to be small enough that it'll fit in your mouth. And here's an example of what a typical dental X-ray might look like. Basically, because the propagation distance is shorter, but mostly because teeth attenuate X-rays more than tissue does, this has a finer pixel size. So let's figure out what determines how to choose the pixel size and the resolution in geometric imaging systems. Computational Imaging. Episode 24, Resolution in Geometric Imaging Systems. So we've talked over the last several episodes about imaging systems that use obscurants to help form an image. In this case, with a pinhole camera, we derived a forward model for the pinhole camera where the pinhole itself acts as the impulse response of the system. When we include the effect of pixel sampling, we get the impulse response from object space is the correlation between the pixel sampling function and the pinhole. So we get a triangular shaped object that looks like this. Here we've assumed a rectangular feature in the coated aperture and a rectangular pixel, and the resolution that we get is equal, influenced by both of those factors. Typically, we'd like to choose the pinhole or the coated aperture feature as small as we can, and then we would choose the pixel pitch to match that resolution, so as not to oversample, but so as not to degrade resolution. So we saw that the pixel, the coated aperture feature size is really, you'd like to make it as small as possible, but as you make it smaller and smaller, eventually wave diffraction will dominate the size of the projected pattern from the code rather than just the shadow of the coated aperture. So the minimum feature size that we could see in measurement space would be the square root of the distance from the measurement plane, or from the code plane to the measurement plane times the wavelength, and then taking the square root. The angular resolution goes like the square root of the wavelength divided by that distance. Now, for X-rays, the wavelength is going to be on the scale of 1 angstrom or even tenths of angstroms or smaller. So that square root of lambda is going to be 10 to the minus 5, 10 to the minus 6 in meters. So delta x, could be micron scale or even smaller if d is smaller. But that's not what's typically observed in X-ray systems. And the reason is that the modulation of the signal in an X-ray system is based on attenuation or scattering of the X-rays over some characteristic length, and X-rays tend to penetrate materials. That's why we can see into materials using an X-ray. So we have this Beer-Lambert law, which describes how the X-ray is attenuated as it moves through the material. What you find is that at any given X-ray energy, you're going from 10 kiloelectron volts up to nearly 100 kiloelectron volts, you have a half value layer. How much material do you have to go through before you would modulate the beam of X-rays by 50%? And this is comparing 1 millimeter thick aluminum with 1 centimeter thick muscle. This is a visual from the website of Peter Spalls, which is a website with all kinds of useful information for radiation imaging. But the key factor here is that to see some modulation on an X-ray beam, you have to go through a fair bit of material, so that's really what's going to limit your resolution. If we think about the sort of geometric model of how resolution is determined, we have the pixel size. If we project the pixel back toward the source, that would tell us how big that projected ray is in the object space. And then on the other hand, the source has some finite size, and typically an X-ray source is going to have it's generated by a focused electron beam that will be on the scale of millimeters. And so either the X-ray source size or the detector size determines what the feature size is in object space. Basically, if these distances are all kind of the same scale, then if I have 100 micron pixels, I would expect to see something on the range of 100 micron resolution in object space. And similarly, if I would like to get in a focused X-ray spot that's on the scale of the features that we're trying to see. What determines how small you make that is noise. That you have to say how many photons are attenuated in each element, and at what level does that become detectable. There are all kinds of studies out there. Here's an example from a group that studied detector pixel and voxel size in looking at microvascular structure. And the top row is a micro CD, where the X-ray is close to the target, and here you're seeing things on the scale from 20 microns to several hundred microns. But you're basically, when you go to smaller sizes, you're going to need to integrate longer to see some modulation on the signal. So you'll get a sharper image, but you'll have exposed the sample to considerably more energy. The lower curves, the lower images, are for whole body CT systems, where the resolution is more on the hundreds of microns or even a millimeter scale. This is comparing a photon counting detector with an energy integrating detector on these scales. So for an X-ray system, resolution is not determined by wave diffraction. It's going to be determined by how much material you need to go through to see some modulation. And then once you know that material size, then you can design a code and a detector to match that. We looked at coded aperture tomographic systems with X-rays, and we found these kind of singular vectors for looking from a single viewpoint. So the feature that you'll see in the code will be proportional to the features that you see in the singular vectors mapped onto object space. In this case, because we're looking from one angle, the feature size is very asymmetric over the object space. You would need to rotate and look from a variety of views to recover a resolution longitudinally that would be close to the transverse resolution. But again, the underlying feature is going to be that we have to think about the feature size based on the number of photons that we detect. In chapter 2, we showed that if we detect a lot of photons, the Cramer-Rao bound for estimation of position in of a point source would be decreased in proportion to the square root of the number of photons detected. But here we actually have to grow the detection area to get to a scale where we'll be able to get resolution. And so the geometric imaging limits actually apply in X-ray systems, and the size of those geometric limits are determined by, for a given material that's under test, how much material do you need to resolve. So next time we're going to realize that there are optics in the world. So we've been through a discussion of X-ray systems, and these have formed great model systems for building a forward model and understanding how to invert forward models to estimate scenes with compressive and other forms of tomography. But thankfully, based on the resolution limits that we've seen, optics is something that is much more sophistication than simply obscuring features. So next time we'll review the geometric theory of optics, and then throughout the next mini set of episodes of this course, we will review a variety of systems that use lenses.